All right, on number 3, I think a sketch is going to be helpful again. I'm going to show a function that on some interval is positive, increasing, and concave up. So positive, increasing, and concave up. There. Now if I were to draw, let's see, I'm going to do this a few times. If I were to draw on this interval a left endpoint rectangle to estimate area, so starting here and ending here, for instance, my left would go up here over, and I would clearly be well below the actual area under the curve. So on this continuum of accuracy, I'm going to put lefties on the far low end, because this is an estimate that is far less than the actual area under the curve. If I do a righty, so there's my interval dotted in, my right endpoint estimate would be far outside the actual area under the curve. So on my continuum of accuracy, I'm going to put a right endpoint estimate way over, it's too big. And my actual area would be somewhere in between. So somewhere in here I've got my actual area. The only thing left is the trapezoidal approximation. And I think the easiest way to see this, because the graph is concave up, if I were to put like an endpoint here and an endpoint here, if I drew a trapezoid in, I'd be just a little bit above the actual area. Not as much as the right endpoint estimate would be. That would give me this much area. A trapezoidal is closer to accurate, but still an overestimate because of the concave up nature of the graph. So trapezoidal falls more than the actual area, but not as much more as the right endpoint. So LATR, see you later. That's what we're looking for. That would be answer A.